el agrado de presentar a ustedes a la doctora Christine Roussel. Ella es full professor en la Universidad de Orleans, en Francia. Su trabajo está enfocado en la combustión, desde los fundamentos de la combustión hasta su aplicación, relacionado con o muy baja emisión o cero emisión en CO2. Especialmente ella trabaja en amoníaco y alcoholes. Ella es Head of International Office and Development for Engineering School en el Polytech Orleans, representante de Francia en el IEA Clean and Efficient Combustion Technical Collaborative Program, miembro del MERI Ammonia International Advisory Board, miembro del programa Committee PIPR Hydrogen, y tiene entre sus múltiples trabajos más de 40 trabajos científicos en colaboración con partners industriales, tales como Renault, Stellantis, Total Energy, Engie, Aramco, entre otros. Hoy vamos a escuchar su conferencia Use of Ammonia as a Clean Fuel, Challenges and Solutions. Ella ha venido en el marco del lanzamiento del Instituto Milenio para el Amoníaco Verde como vector energético, del cual nuestra universidad es una de las 4 albergantes, junto con la Pontificia Universidad Católica de Santiago, la Universidad Austral de Chile y la Universidad de Talca. Este instituto es dirigido por su director, que es el doctor Mauricio Isaacs, y la que les habla es la directora alterna. Dejo con ustedes a la doctora Christine Roussel.
Muchas gracias.
Christine.
Sí.
¿Tienes?
Sí. ¿Sí? Sí. So I changed a little bit the title, but it's the same content, in fact. So I know that most of you are chemists. I'm not chemist, so sorry. My specialty is about combustion. So you can say that in combustion there is chemistry, but I'm not specialist of chemistry of combustion. I'm more specialist about fluid mechanics and engine, internal combustion engine. So I come from University of Orleans. Orleans is 100 kilometers below Paris. And it is a university, medium-sized town, and also medium-sized university in France because it's 20,000 students. And my teaching department is engineering school, and especially about thermodynamics, energy on engine, on aerospatial. So I will try to convince you that finally ammonia is a good fuel for the future that we can use also in internal combustion engine. I will change my presentation. It is not the same that I did yesterday, but perhaps some of you don't know very well what's happened in Europe. So what it is important to know, it's in fact in Europe, the European Union decided as objective to be the first continent to be neutral in greenhouse gases in 2050. So it means that we cannot emit more CO2 that we can absorb through the forest and the ocean. So this is very difficult because it's not only on the energy sector, it's also for the transport, it's also for the industry. So it means that we have to change totally our mind, and unfortunately the first consequence is Europe banish internal combustion engine vehicles, and they announced that in fact we have to have only electric vehicles for 2035. In reality, I hope that this will never happen, and perhaps you know that due to some German company and German people, researchers, we signed also a lot of petitions for Europe Union to say, be careful, zero carbon emission vehicles doesn't mean only electric vehicle. It means that we can certainly use zero carbon fuel, like hydrogen or ammonia, and also electrofuel. So electrofuel, it means that we can produce fuel with hydrogen and CO2 that we can capture from any combustion plant that we will still have as example for the waste. So we can do it. Anyway, so my research institute, the name is PRISM, and I am especially involved in the energy combustion engine department. And from the last 30 years, we work only in internal combustion engine with classical fuel. And changed my mind since 7 years to more focus on e-fuel like hydrogen, ammonia, but also alcohol or XTL, so it's a synthetic fuel, okay? And also some sub-products like acetone, butanol, ethanol, because when we want to produce butanol, okay, for the crops, when we want to produce butanol, in fact, there is an intermediate step when we have a mixture acetone, butanol, ethanol. And the idea is to say, if we can use directly this as fuel, we don't need to have more chemical process to obtain butanol, so it's less expensive. And it works. We do a lot of work with Thailand and Vietnam on that, for example. Anyway, my main objective is sure to try to convince that we can use this kind of fuel in internal combustion engine, but for that we need to understand what's happened when we use this fuel in comparison that we use gasoline or diesel. In the case of ammonia or in the case of hydrogen also, it is really different than conventional fuel. What I want to say, when we use synthetic fuel, one idea is to try to have similar properties that we can have with gasoline or diesel. So we have some difference, but it's not so huge difference. In the case of ammonia and also hydrogen, there is no comparison. So it is also that we have to convince sometimes that engine manufacturer, because you can have some engine manufacturer for trucks. They have a long time experience about diesel engine. They know diesel engine very well. But when they want to put natural gas or hydrogen or ammonia, they cannot think that it is like diesel. It's not a diesel engine. It's not diesel combustion, even if we use the same engine. Okay, on this, it's only we need to educate them also. So for that, it's clear we have not only engine bench with a dynamometer. This could be interesting, but not so much for me because we cannot understand very well the phenomena. And one I like is to understand the combustion process, the injection process, all process that we have in the combustion chamber. So for that, an example of some visualization that we can do inside the combustion chamber of the engine to understand the process in order to optimize them, but also to provide sufficient accurate data for develop, validate modeling, CFD modeling, and that will help in fact the design of engine for the future. Okay, so we have some classical benches, but it's only here it's only single cylinder. So I don't care about multi-cylinder. I don't care about real problem that you have technically in the engine. It's not the objective. So it's not exactly true because when you want to use ammonia, it's so special. So I think that you know ammonia is liquid at 10 bar, but below is gaseous. If I have a bottle of ammonia in gaseous phase, when I take some ammonia with high flow rate to fill my engine, as function of the power that I need, all the line is totally frozen. I have ice, I cannot have ammonia. So even if I say I don't care about what's happened around the engine, it's not true. We have always to find some solution in order to fill, in fact, the engine with ammonia. With hydrogen, it's different But in fact, we have some other problem also, because hydrogen is very small molecule, the diffusion rate is very high, so we can have, in fact, hydrogen can go everywhere in the intake port, and we can have a big issue about what we call flashback, so it means that we can have combustion in the intake port. So it's a very different. Okay, so in fact, in engine, it's very complex. It's fluid mechanics, thermodynamics, chemistry. So we have first the flow field inside the combustion chamber, emission, mixture preparation, in order to have the meeting between the air, the oxidant, and the fuel. We have flame development. We have wall heat loss. It will be the same if we use hydrogen, ammonia, or classical fuel. The heat losses are totally different because, as function of the fuel, the flame can be more near the wall or not. In the case of ammonia, is not. In the case of hydrogen, yes, it is. So we will have also a lot of problem about material capability for the long time. Okay? So, to better understand, we did some other experimental setup. So it's very complicated experiment setup. Even at the beginnings, we think that it is easier than engine. We have something that we call rapid compression machine. The objective is only to determine auto-emission delay. In the case of ammonia, before the last 10 years, we never study ammonia as fuel. There are some, I will show you, there are some experiments in vehicles, but we don't know fundamental data, especially the chemistry. So to develop accurate kinetics mechanism, we need data as function of temperature, pressure, equivalence ratio, or dilutant, or third body, and so on. So it's for that we need some other experimental setup, like rapid compression machine. We need also to inject ammonia. What we will do for the next step, it will be to inject directly in the combustion chamber. So we have to do with some injection to the spray what it will be ammonia. Ammonia is not a classical fuel because the pressure of saturation pressure is totally different. I told you 10 bar at 20 degrees, we change between liquid and gaseous. With gasoline or diesel, there is no issue, we are liquid phase. Okay, so we have some phenomena that we call flash burning. This will change totally the mixture preparation inside the combustion chamber. And we have also some fundamental vessel in order to study the propagation of simple flame or also interaction with the turbulence. So if you are lucky, we have seen that it is a red flame. The red flame, it's a typical ammonia flame due to the presence of NH2 radical, NH2 star. It's chemiluminescence. So it's totally different to hydrocarbons 1. Hydrocarbon 1 is mainly blue, okay, due to CH star, or it could be yellow in case of diesel due to the soot luminescence, okay? And with hydrogen, normally in premixed we cannot see the flame. So it's also one thing very dangerous because we never see the flame. It is premixed hydrogen air flame. If it is diffusion, we will see also some red due to the high temperature emissions of water. And also, we are lucky, we have what we call optical access engine. So it means that we can look what's happened inside the combustion chamber itself. Okay, so normally we work only in the engine, but as you can see, this kind of experimental setup helps to understand process, more fundamental. So it means that in fact the data can be applied as function of the temperature, pressure, equivalence ratio, and so on. So conditions can be extended to optimize also CFD for gas turbine. Okay, so if you know a little bit ammonia, it's clear that between there is no one solution. If we consider that the future as want European Union, for example, would be only to use renewable energy. So in France we are a little bit particular because for us there is nuclear. It's a clean energy if we consider greenhouse gases. So we can consider it inside. Anyway, when we have renewable energy, sure, we have different possibilities. Mainly we want to use it as they produce electricity, and we have to share the electricity in a smart grid in order to optimize the system. We can also storage this energy when it produces too much that we cannot consume straight away, or we cannot storage in batteries. We can storage in a chemical phase, so it means green hydrogen. We can also storage in the other type, so it's the other hydrogen, it's a green ammonia. And the advantage of ammonia in comparison to hydrogen, it's due to its physical characteristic. It allows higher storage duration, so long storage duration, and also long distance distribution. The cost is reduced when we use ammonia. It's the main purpose. It's for that we want to see what's happened with green ammonia. It's the advantage when we are until the use. Okay? If I am in the production, sure, the production of ammonia costs higher than hydrogen, but we win when we consider long storage and long distance distribution. After, even electricity, hydrogen, ammonia, we can use in very many things because we can retrieve electricity, so it's power to hydrogen to power, or power to ammonia to power, or we can directly use them as a fuel from fuel cells, or also in internal combustion system like engine, gas turbine, or also now we try to see what will happen in burner. Okay, so if we consider that ammonia is a very good hydrogen carrier, okay, due to the fact that it costs a lot for long storage and long duration transportation, how can we extract the energy content in ammonia? The first idea was to say we have a lot of hydrogen inside ammonia, we have to extract the hydrogen. Okay? But perhaps it's not the best solution. Always it depends on the application. If the application is to have the power to power, perhaps it's better to have the intermediate step of hydrogen. It is interesting that in fact, it is a long time ago now, if I remember, researcher from UK, it was 10 years ago, announced that in fact, sure, ammonia is a clean and secure hydrogen containing energy source. It's secure because in fact, ammonia is not a very good fuel, so it means that we have less problem about detonation that we have with hydrogen. So for that is more secure. But they propose, it was University of Oxford, they propose the idea to use directly ammonia in engine. It was also the same in China. They also underline that ammonia is an ideal fuel since it is not a greenhouse gas and in complete combustion will form only nitrogen and water. It's not totally true, but if we consider only complete combustion reaction, it is. So, first, to decompose ammonia by means of new optimized reactor in order to provide hydrogen, to use ammonia directly in fuel cells. For the moment, it's only in research TRL very low to do that, because for the moment there is no fuel cells that they can admit ammonia directly with high efficiency on long-term duration. It's not, there is no for the moment in the market, and even in some innovation, or to use the chemical in combustion systems such as gas turbine or internal combustion engine. So, what's about ammonia as fuel for internal combustion engine? Of course, it's a joke, but ammonia as fuel for vehicle, it's a whole story. And the first ammonia engine is a French engineer, de Laporte. But we can see that in fact it's not a combustion engine, okay? It's only due to the phase change of ammonia, as I told you, because 9 bar we change, so if we decrease the pressure, we will be in vapor phase, okay? So it's like a machine à vapeur, okay? So it's very different, but it's an engine, so it's a joke. Anyway, ammonia as fuel phenol is a very old history. So it starts in Norway in 1933, but we don't have any things about that, so I don't know exactly, I have no story about that, but they convert a truck to run an ammonia. I cannot say how many ammonia there is in the truck, in the engine, with the diesel and so on, but what we know more is this one. So it was during the Second World War, when in fact there is a big lack of fuel. And in Brussels, a Belgian company decided to fill in fact their engine with ammonia and also synthetic gas from coal. So they have a lot of miles. It was a success, but we don't know how many ammonia. Perhaps 20%, but perhaps 30%. And you can imagine that the legislation and the standard was totally different. Now we cannot do like that because we have a lot of standard about emissions. Not only CO2 problem, we have the other emissions like NOx, hydrocarbons, CO, particulate matter, and so on. So we cannot say, okay, we do exactly what we did. Is not true. During the 60s, there is a new interest about ammonia as fuel only from USA. Because in fact US produce a lot of ammonia for fertilizing, and they have a surplus of ammonia. They don't know what they can do, so if perhaps we can do as during the Second War. So they did a lot of study in order to see if it is possible in engine, in gas turbine. The unique thing that we can remind is that they do a rocket with a record, because it was a 200 launches, okay, with liquid ammonia and liquid oxygen. And also they try with different other aircraft, like helicopter or this kind of aircraft. They really go, I will show you briefly after, they try really so to optimize the tank and so on. Really, it was nice work. But after, no interest about ammonia, we produce ammonia only as a fertilizer, so we don't need to do what we can do with it. So I don't know exactly what it started again 10 years ago, 15 years ago, at University of Michigan, but there is a pickup where there is an ammonia tank, and in fact what they do, they mix ammonia with diesel. And there is also this nice realization in Pisa in Italy. They work a lot with a small engine in order to see how it's possible to use only ammonia, and they conclude that it's not so easy, so sometimes we need to add his brother hydrogen. And okay, so there is some other, it's only 70% of ammonia. On more recent projects, it's about tractor and also about trucks. Okay. Engine, two types of engine we have around the world. We have a spark ignition engine with gasoline fuel, or we have combustion ignition engine with diesel fuel. Okay? In fact, from all the previous study that I show you, it's clear that to use ammonia in spark ignition engine, we need something, because its characteristic, I will show, is not good. So we need something to ignite it. So a very good ignition system, or what we call also a combustion promoter. In the case of combustion ignition engine, I already told you that ammonia is resistant to auto ignition. It's for that it's good for security. So you can imagine that if I put in engine, no way, it cannot start. So also, I need an ignition promoter. I can add a spark plug inside the engine, or I can have a solution to help the combustion with the mixture. So it means with some diesel somewhere inside the combustion chamber to ignite, in fact, locally ammonia. From the previous study, there are a lot of things about the mixed with gasoline, diesel, biodiesel, DME, natural gas, methane, alcohol, and more with hydrogen. Sure, because what we want, it's clear, we want to decrease the carbon footprint. So this is not good. It's only partial decarbonization. So if we want full decarbonization, if we can run pure ammonia, we will. But even if we can run pure ammonia with a small quantity of hydrogen, it's good. Okay. In fact, if we look on the website, there is a lot of announcements. Less and less about a car, trucks, because unfortunately, to use ammonia is not so easy because ammonia is a toxic gas. So we have to avoid any leakage on any unburned ammonia, especially if we are on the street. You can imagine it is not possible to have that. So it means that even if we work with engine from automotive company, we know that this will never be realized. So it will be never on the road. But it's very different if we consider the marine sector. So in 2019, it was the first time, so remember I told you that in fact European Union did a drastic objective for 2050. So it means that for the moment transport emit too much CO2. Okay, terrestrial transport, so cars, trucks. But when we will finish with them, we will have train, we will have marine, and we will have aircraft. The impact of our CO2 emission will increase. Okay, so in 2019, the International Maritime Office, for the first time, drew a roadmap in order to decarbonize the ships. It was the first time, so it's really only 4 years. Moreover, International Maritime Office is not like in US or in Europe about standards for car or trucks. It's only something like informal office, you know, it's not for regulation. It's okay, we will decide to do that, but that's it, there is no obligation. This is totally different. It's only some announcement. For the moment, there is no standard which oblige this sector. So, what from that, ammonia becomes very interesting as fuel for marine, because we have less problem if we have any leakage. We are on the ocean. It could be a problem with the fishes. So I joke, but sure, there are some studies, or they try to see what will be the impact on the water biodiversity. And this is the announcement. Sea job, it's a naval group, so it means that they have some ships also. The first green ship fuel, the Viking energy project. This is a man energy solution. And also, it's a really famous researcher about ammonia. And he tried to see the economic evaluation of ammonia fuel for short sea shipping. So what we can see also, here it's a short sea shipping, here it's another kind of ship. So this, it's for different size of ship, but there is not only one solution, it will be also a mixture. On the sea we will have some ships with hydrogen, some ships with natural gas, some ships with bioethanol, some ships with methanol, and some ships with ammonia. It depends of what we do with this kind of ships and how big they are. What we can see from some recent publication, for example, that in fact there are no experiment result of ammonia-fueled mid or heavy-duty engine, including marine diesel engine, and there is a lack of study to show the benefits of ammonia for maritime transportation. What does it mean? In fact, I show you briefly some picture of engine that we have in our lab. It's engine for cars. So the size is like that. It's a 4-cylinder, and we use only 1 cylinder, but it's like that or like that. So it's normal size, like you have in your car. Marine engine is not like that. First, it could be at least like that, or until what we call cathedral engine. So it means that it is 4, 5, 6, or 7 meter high, okay, with 15, 20 meter. So it means that there is no research institute or university with this kind of engine. So sure, it's difficult to obtain data because the problem is in fact when they want to change a fuel for marine sector, they change directly in a boat. With ammonia, you cannot do that. It's so complicated to change because we have different about fuel storage, we have difference about injection, we have different about combustion. So they don't want to do that. They want to know if it is possible and realistic and economically feasible. So it means that in fact we are lucky because they need our data at least to validate their first step of CFD modeling in order to try to see if they can in fact use for their design engine. What they know only for the moment, it's in fact what I'm sure it will work is that. This is not so difficult. It's what we call real dual fuel. It means that we mixed, in fact, we have a diesel engine with diesel oil, and we will put one quantity of ammonia. Until 60%, I don't know, but until 40-50%, it will work. There is no big issue. The issue will be about the pollutant emission that I will show you. But it is not the objective. As I already told you, the objective is to decarbonize. So if we want full decarbonization, we need to decrease as well as possible the hydrocarbon content. So other possibility that we want to do, it's at least this. So it means only 5% of diesel oil fuel. This is challenging because we don't know. Okay. There is also a very recent announcement where in fact it's Malle says that ammonia is a clean diesel replacement. This is nice because in fact, even if I don't know exactly what they do until now, what it is nice, it's in fact, you can imagine when we announce that we stop all engine. and we will go to electric vehicles, it means that we have a lot of trouble about the production of engine. We have to stop everything in Europe. Okay? When Mahler announced this kind of announcement, it means that in fact we can use regular diesel engine and to use ammonia instead of diesel. So this can change totally some application of engine. So this is EV duty trucks, so it's for trucks. Okay? So it could be one solution. Okay, so in fact, we have three possibilities. We say, okay, we want to retrofit diesel engine. If we want to retrofit diesel engine, in fact, we can continue to use a pilot diesel injection in order to help the combustion because ammonia is not so good, or we can add a spark plug in our diesel engine. Or, if we want to use a spark ignition engine, we need to optimize it, especially to increase the compression ratio. Okay, there is more and more and more, but not only about marine sector. We can see also that there is new announcement about some aircraft. So this is funny. Okay, how ammonia is relevant to be used in engine in comparison to classical fuel. So first, it's boiling point. Hydrogen, if we want to storage in liquid phase at ambient pressure, we need very high cryogenic power. Ammonia, it is also cryogenic, but you can see it costs very less. And this, it could be like we can have for DME, or it could be also what we do for liquefied natural gas. Okay, the density, it's not so far for what we can get with methane. So if we can take one diesel engine who already is retrofitted to use with natural gas, we can imagine that it could be possible to use it for ammonia. Standard storage form, so this it depends. It could be gas, it could be compressed gas, it could be liquid, so it's not totally true. And ammonia is liquid. So it's not necessarily liquid at cryogenic form, it could be also only with pressure until 20 bar, for example. Storage density, is not so bad. It's a big issue with hydrogen, but with ammonia, it's not so far that what we can have for classical fuel. Unfortunately, there is a big problem. First, you can see heat value, megajoule per kilogram. You can see that ammonia is not good. Okay? It will be the same with ethanol. Especially if we compare with gasoline or diesel, is the same. We can see that it's at least 2 times lower. Sure, if we compare with hydrogen, you can say, wow, hydrogen, it's good. But be careful because it's in mass. In volume, is not true. Okay? So, in volume, we have some problem with hydrogen, it's too low. And we can see that it is a little bit better now for ammonia, and it is similar to what we can have with methane. Another thing is very important is that heat of vaporization. We know that most of the system, it is not only for engine, it will be also for gas turbine. We will try to inject in liquid phase, okay, to have liquid injection or fuel. But we can see that the heat of vaporization for ammonia is very high in comparison to other fuel. So it means that when we inject inside combustion chamber, we will cool down a lot the temperature inside the combustion chamber. As function of what we want, it could be an advantage or a drawback. It depends. For example, we just measure the temperature when we inject. It could be until minus 60 degrees. We inject an ambient temperature, it's 20 degrees at 10 bar, and it is minus 60 degrees that we have in the jet due to the heat of vaporization. Okay, fuel consumption for transport application. So I told you that NH3 is 11.5 megajoule per liter. So one single storage tank of 40,000 meters cube of NH3 corresponds to annual electricity demand of 30,000 households. So it's not so bad, in fact. But it is important, if we consider a car with a tank of 70 liters of gasoline, to provide the same energy, this is the tank that I need for hydrogen. And this is the tank that I need for ammonia. Sure, it's increased, okay? You can see it's more than 300 liters in comparison to 70 liters. For diesel fuel on the 4 trucks, it's not so good because we can see that 400 liters, it means that we need 1.1 ton in mass of ammonia. Okay? We can see also it's 3.4 ton in mass of hydrogen. And this is also a big issue because until now, for example, Air Liquide produce and transport hydrogen around the world. It's a leader. Not only there is Linde aussi, and it's only a leader, but anyway. And when we want very high quantity of hydrogen, it's complicated because it means that we need trucks. If we want to run the other with hydrogen, it is not possible. It can only transport what he can use. So there are a lot of things to think. So it is the same, but when we consider, in fact, ships, so this is low sulfur fuel oil. Okay, it's the reference, 1 volume. It means that for liquefied natural gas, we multiply by 2 around. Liquefied propane gas, petroleum gas, by 2 also, but with methanol also it's 2.5, ammonia it's 4. Hydrogen, it depends if it is cryogenic, compressed at 350 bar or 700 bar, it multiplies between 6 and 10. And if you want to do the same thing with battery, something here. So, sure. But it depends also on the size of the ship. Okay, before to focus perhaps a little bit more on the engine, I want to show you a little bit what did the US Army during the 60s. So they tried to use ammonia for helico and wind aircraft. And they do very nice work because it is the first study when you can see what they do in order to optimize the fuel tank and so on. So they try to evaluate how it could be possible due to the problem of the weight. You can see when I show you if we replace gasoline, diesel in a truck is 1.1 ton of ammonia that we need. It's not possible. So it is worst when we have aircraft. We cannot have this kind of mass. They try to optimize. And first they work on materials for fuel storage, so for ammonia storage. And they show that at the end, Inconel 600 vessel is the better due to higher strength and lower corrosive properties. Because also ammonia is not only toxic, it's also corrosive. So this means that it's the best materials for suitable long-distance missions. And they try also low high-pressure tanks, cylindrical and spherical geometry. And they conclude that cylindrical tanks is more suitable at low pressure due to the high tight insulation vital at cold ignition conditions. After, they have to deal with the flow rate because we need energy when we have aircraft. So the flow rate is 2.4 times higher than when we use aircraft fuel, so kerosene. And this is very difficult also to deal because we have to change all the flow rate system. And they use partial dissociation of cracking. So it means that inside, in fact, before the combustion chamber, they tried to crack partially ammonia. It was 28%, okay, in nitrogen and hydrogen, in order to have some flame properties similar to what we can have with kerosene. This is good because, in fact, it increases the lower heating value, okay, and induce, in fact, a decrease of the specific fuel consumption. So it means that we need a little bit less ammonia. They obtain a very good, in fact, result because they have a maximum power increase of 15%. And they increase the heat capacity of combustion products, mainly hydrogen. So at the end, the thermal efficiency was improved in comparison to kerosene. And it was the conclusion from the 60s. It's good. They enhance the performance, but in fact, it's too complex to control, too complex the fueling system, and this predicts higher costs relative to development, procurement, and installation. And it was finished. But it was during the 60s. So now we totally changed the objective. So it's for that there are different projects. There is a big project with some university in US and Boeing. They try to see how it is possible. There is one small project, a small company in Australia. And there is one other one, I don't remember, somewhere in Europe. But when I say that in France to Safran, or Safran it's a link to Airbus, they say, oh, you are totally crazy. We don't want. We prefer hydrogen. So when they say that, we laugh, because hydrogen in a plane, it's like a bomb. Okay, so, okay. What's about ammonia combustion characteristic? I don't know what is the time. I don't know at what time I have to finish. So you know, I'm a teacher, so I can. Okay, I will go faster. So when we look also about the combustion properties, we are chemists, most of you, so in fact you know combustion reaction. I think it's not so difficult. Fuel plus oxidant, okay? When we have carbon fuel, give CO2 plus H2O, okay? In the case of ammonia, it is H2O plus nitrogen. If I do I balance the equation, I obtain the stoichiometric air-fuel ratio. So it means that for 1 kilogram of air, I need, no, it's not that. For 1 kilogram of fuel, I need about 18 kilogram of air. In ammonia, for 1 kilogram of ammonia, I need only 6 kilograms of air. The consequence is not good because it means that my fuel consumption is multiplied by 3. Okay? So it's not good for that. If I look about the flammability limit, well, it's not usual, but it is not so far from gasoline. So it's okay. If I look on the combustion velocity, so it's a fundamental parameter that we determine when you show at the beginning the flame, orange flame. You know, in this setup, we determine this fundamental parameter. We can see that, unfortunately, this is very low. It's 7 centimeters per second. So it means when in my combustion chamber, I ignite my ammonia air mixture, 7 centimeters per second, it's propagate. So it's very, very, very slow. You can see the difference with hydrogen. Okay, but this is not good. Hydrogen is too much. We have to deal with that. We cannot burn at this velocity. So we need to slow down, in fact, the velocity of hydrogen. And this is what we have, for example, with gasoline. So it's a 40 centimeter per second. It's not sufficient because this is a laminar. So it means in my combustion chamber, I have only quiescent atmosphere, okay? In engine or in gas turbine, it's not like that. I have some vortices, a lot of vortices inside. What I need vortices, due to vortices, in fact, my flame, which is very smooth, will be wrinkled, okay, like that, everywhere. When it is wrinkled, my combustion speed is increased because my fuel consumption rate is increased, okay? So, in fact, what I need is not 40 centimeters per second, is more. But this is due to the interaction between the flame, so the chemistry, and the turbulence, okay? And ammonia is so special that when I put turbulence inside my combustion chamber, it's totally different when I put gasoline. And in fact, at the end, I can enhance sufficiently, in fact, the combustion propagation speed. Research octane number, perhaps you know, auto-ignition temperature, you can see it's also very high. So it means it cannot auto-ignite. The study from the US during the 60s calculates that it needs at least a compression ratio of 35 to have auto-ignition of ammonia. 35. Usually, gasoline engine, it's 10, 10.5, 11. Diesel, it's between 14 until 18. So you can imagine 35. Or we need to have a very big turbo to have a very high boosted conditions. Okay, so it's not realistic. But in the other hand, if we look, the research octane number is very high, so it means that it's good. We have no problem about knock. Okay? And the flame temperature, so it's not Celsius, it's Kelvin, sorry. The flame temperature is a little bit lower. It could be an advantage because, on point of view of chemistry, it means that we have less thermal NOx production. Okay, so exactly what I said, it's okay. I will try to go. So, no CO2, no CO, no particulate matter, no hydrocarbons, good energy density depends, potential for high compression ratio. The first question, do we need a combustion promoter to enhance the performance and ensure combustion stability? And the main problem also, it's about emissions. Because even if I said, okay, adiabatic temperature is a little bit lower, so a little bit less thermal NOx production, NH3 has nitrogen in the fuel, in the molecule, so it means that we can have other process to produce NOx. It's not only NOx, the other problem is N2O. And N2O is the laughing gas, so it's very good for teenagers, they like it. But the problem is the greenhouse effect. It's 300 times the equivalent in CO2 after 100 years. For comparison, methane, it's 35. So methane, it's 35 times the impact on greenhouse effect when compared to CO2. Ammonia, it's 300. And also, already I told you, we have avoid any NH3 emissions. It's not possible. So we need some mitigation strategy for pollutant. And moreover, it's corrosive, so we cannot have any copper, alloy, plastic, rubber, Teflon. It's not possible. Okay? And it is toxic at 300 ppm in air. Okay, so it's not good for health. Okay, so you can imagine that it is a big challenge. From the past of, no, this I will let, it's too complicated. So, best possibility to use ammonia in internal combustion engine, it's really complex and complex and complex. Because, okay, I have ammonia tank, okay? I think that it will be in liquid phase because it's better for storage volume, but I can use it in gaseous or liquid. Don't forget, if my tank is at 20 bar, I need only to be at 9 bar, I am in gaseous phase. So it means that I can inject directly in gaseous phase. I can inject in port fuel injection, so in the intake port. I can inject directly in the combustion chamber. I can inject per fuel injection plus another injector directly. So you can imagine the combination between a gaseous, liquid, where, how. And if I consider spark ignition engine, it will be not sufficient. Okay, so I need a very strong spark igniter system, so boosted ignition system, or to be helped with another fuel like hydrogen. The main problem will be that it is really difficult to have engine at very low load. It is very difficult to start the engine with classical spark ignition engine. So, if I want to add hydrogen, I have different solutions. I can say, okay, I have another tank. Perhaps in ships, everything is possible. If we consider a truck, it is not possible to imagine that we will have 2 tanks. So the best way is to imagine that we will have onboard cracker in order to have a small quantity of hydrogen, and this can also be on the demand. So for example, recently Toyota did a study with a total solution, so ammonia tank. There are electric cracker of ammonia, a thermal one. Okay, so at the beginning when they start the engine, in fact they put 90% of ammonia in the electric cracker, the reformer, okay, to have high quantity of hydrogen, to fill, in fact, the engine in order to heat up, and to be sure that we can run a stable condition at low load, so at the beginning. When the engine is sufficiently heated up, in fact, the exhaust gases temperature is increased, so they can use this energy to use the partial reformer, which is in thermal, not electric one. Okay? But you can see that it is really complex, so we have some other things to control again. Or if we use a diesel design engine, sure, we can do the same. We can add a spark plug with a small hydrogen or not. But also, we can use a reactive fuel by maintaining, in fact, the diesel injector. So we fill with air and ammonia, and we inject directly the diesel, very small quantity. And we can see that due to that, as diesel fuel is very reactant, we have local site of auto-ignition. So, yes, it is already that I say to you, we have a lot of solution. First for injection, and this is a first result that we have done at the beginning when I talk you about what is the problem with ammonia injection. In fact, look only in this column, or only in this column. So it's a real injector. We use an injector for gasoline, a Bosch one, 7 hole. We change nothing, and we try. So what we can see, so this is a function of the condition where we inject, so ambient conditions. In here it's a saturation pressure curve for ammonia, and this is, for example, for gasoline, ethanol. You can see it's totally different. So if we are here, okay, and we inject, what will happen? In fact, we will straight away vaporize ammonia. It's not so simple because, as I told you, we will have a decrease of temperature locally. So it means minus 60 degrees Celsius. As we decrease the temperature, what's happened? In fact, we will become again liquid. So it means that it will be always a balance. It's not a continuous phenomenon. It's not continuous vaporization. It's really what we call flash boiling. So straight away, we have, in fact, the vaporization of the liquid fuel, but it's cooled down the ambient, so we cannot, in fact, vaporize what we inject, and the temperature increase again, and so it's not continuous phenomena. What it is important is to see the difference of the spray, liquid spray, in comparison to what we have with gasoline. You have different jet because it's a 7-hole, but here you cannot see. So really, the injection is totally narrow. So you can see that you can imagine when we want to inject in gas turbine or in engine, we have not the same air-fuel mixture locally. This will be very affected by the flash boiling phenomena. And when we increase the ambient density, okay, we can see also that here we have a lot of small volutes due to, in fact, the vapor phase. But you can see that it is also so different than what you can get with gasoline. In gaseous injection is better, and in fact there is only one study, but what they conclude is, in fact, it's really similar to what we can have with gaseous methane, so there is no real issue. Sure, the difference will be the local equivalence ratio due to the change of the stoichiometric air-fuel ratio that we have with ammonia. But it is similar. So this is easy. It means that, in fact, we can use similar injector and we can use same model. Okay, this is for injection, but it is not result for the moment. But I show you that it is, the flame speed is very low. So many people say, oh, it will be better with lower engine speed. I'm not totally convinced. It's limited due to the narrow flammability limit on flame speed. So in complete combustion, misfire, how we can improve the ignition system and how we can also enhance the mixing. So I want to, this is too complicated. So this is an example of setup that we use. So it's a regular engine, or it is not, it depends. But what we can see, in fact, we don't, for the moment, we don't use injection system. So it means that, in fact, we mixed ammonia, air, and ammonia, air, hydrogen in a plenum in order to have not the problem about the injection. Okay? And we look at what's happened, and we have FTR in order to measure emissions. Okay. What it is interesting, it's in this kind of engine, so it's a regular one. How many? 3 minutes? 5 minutes? 2. Okay, in this kind of engine, in fact, it was not possible to use ammonia without a small content of hydrogen. Only when we have higher than atmospheric conditions, so slightly boosted conditions. Okay, this is a boosted condition, 1.2 bar, okay? And what it is interesting, it's we have a best work for slightly rich mixture. So no clean condition, so it's better because we will avoid NOx emissions. And if we compare with methane, it's quite similar power that we can get, okay? And also this is the reference with gasoline. So it means that, in fact, the efficiency is better. as already we show with the aircraft. Okay, so we did a lot of things. We try to see what's happened with a standard spark ignition engine. We change the compression ratio, or we use diesel engine, so it means with higher compression ratio, when we add, in fact, a spark plug. And we try also to improve the combustion chamber shape. So perhaps you don't know, but the main difference between spark ignition engine and diesel engine, sure, it's the fuel, but there is a consequence of that. The main difference is, in fact, the flow field inside the spark ignition engine is like that. We call that tumble, okay, in order to have vortices to enhance the combustion. And in diesel, the combustion chamber is like that, to have a motion like that. We don't produce vortices. In fact, you do that to help, because direct injection of diesel to help the combustion, okay? So it's totally different. So we can imagine that we have totally different results. We try to, yes. So here, for example, it's about emission. This it could be interesting. This is unburned ammonia, and this is NOx. So it's good. When you are slightly rich, NOx is very, very low, okay? So there is no issue. But when we are slightly rich, what's happened? We have an increase of ammonia. We can see that even if I am in a lean mixture, I still have ammonia. And this is not good, okay? So it's for that post-treatment will be very important. So if some car manufacturer or engine manufacturer comes to see me and they say, oh, what is the best mixture that we need for ammonia? It's very difficult to answer, because here I have a minimum of ammonia, but I have NOx. And here I have less ammonia, but I have no NOx. So it is what I showed yesterday. We have two solutions. If we have NOx and NH3, we can imagine by it the temperature at the exhaust, we have what we say reduction of NOx by NH3. It's what we call SCR, selective catalytic reactor, that we use usually in diesel engine. Okay? But it is not so easy, because this is one case, one power. Okay? If I change the conditions, the ratio between NH3 and NO will change. So this reactor will be less efficient. Okay? If I do that, when I have no NOx, so this is nice, I still have a problem with NH3. So for that, I need catalyzer of NH3 in order to oxidize it in post-treatment. So there is plenty of things to do for chemists. It's my conclusion. So I think I have a conclusion somewhere. I don't want, perhaps. Yes, it's this one. I think it's finished. Okay, thank you. I hope it was not so complicated. I tried to explain.
Bueno, yo quisiera entregarle a nombre de la universidad. Es muy pequeñito el regalo, pero para que se lleve un recuerdo de...
Muchas gracias. Merci beaucoup. Merci. I hope that you understand something, because I know that it's not your specialty, so I try. Oh.
No, it's okay.
It's okay? Don't hesitate if you have some questions.
I have just one question.
Yes?
Can you imagine a cylinder with ammonia and hydrogen as the fuel, and not in separate the...
No.
It's possible to have this in,
No.
in one, why not?
No, because due to the temperature phase is not the same.
Yeah.
Okay? And I don't, you can mix it, sure, but I don't think that you can store it a long time.
Yeah.
Moreover, it is always complicated with hydrogen, because even if when I do that, because hydrogen is a very high diffusion rate. And for example, in some gas turbine, okay, they inject a mixture. They inject a mixture of 70% ammonia, 30% hydrogen. They do that because it's the same combustion characteristic, laminar flame speed, than methane. So for engineers, they say, yes, it's the same characteristic, it works. So they try to do that, and they simulate it with fluent. What's happened? When you inject inside the combustion chamber, due to the difference of the diffusion rate, hydrogen goes everywhere. And in fact, the flame will also follow hydrogen, and we are looking at a very high temperature. So it's not good also to do that. It's better to manage locally the mixture.
Thank you.
Yes?
In selective catalytic reduction,
Yes.
you talked about diesel after burning process, like
Yes.
cleaning the gases. But I have heard that there is a process that uses ammonia to reduce the NOx.
Yes.
So you refer to that or to conventional diesel catalytic converter?
SCR, it's for diesel engine. So in fact, in diesel engine, we have a small tank of ammonia already in the car. It's called AdBlue. Okay, it's urea.
In all diesel engines?
In France, yes, it's Euro 6.
Yeah.
I don't know in Chile, but I think the car is not old also. I have seen on the road, so I think it's not so far. So I think it's also the same. So yes, all cars have a small tank of urea and also selective catalytic reactor on the exhaust to reduce NOx with urea, so with ammonia. It's another way to storage ammonia.
All right. And the temperature to reach this reduction?
So it is one problem, yes. I think it's 500 degrees Celsius. I think. So sure, in diesel car, we manage, in fact, the flow rate of ammonia. In fact, there is a control unit calculator, okay, ECU, and we have the mapping of the engine as function of the power, the NOx emission on NH3 and so on. And in fact, they manage the flow rate, the injection of NH3 in the exhaust. They have a small injection of NH3 as function of the operating conditions. They know the NOx that we will have, and they adjust the flow rate. Okay? The problem with ammonia engine, the ratio between NH3 and NO can change a lot. So another idea is to have also an injection on the exhaust of NH3 to counterbalance this variation, to be sure that we keep the right ratio. The right ratio, it has to be the same quantity, if I well remember. It's NH3 divided by NOx has to be 1. The same molar volume, molar, okay, composition. Yes?
¿Se escucha? Thank you for your nice presentation.
Thank you.
I have a question about the cost and the competitive, all the economy of green ammonia against the fossil fuels. Today, what are the most important costs in the application of this technology in comparison to the fossil fuels?
So first, until now, there is no system on the road, as I said, so it is difficult to have this kind of answer about the cost, because it has to be a choice to favor, in fact, this shows when we will enhance the machine, the cost will decrease also, okay? After, in comparison to hydrocarbon fuels, in fact, it's not a problem of comparison of hydrocarbon fuels. We have a big problem, it's the climate change, so we have to do something. If we have to do something, we have to stop to have CO2 emissions. So it is not a problem of cost, because sure, hydrogen, ammonia, e-fuel cost a lot for the moment, okay? Because it is not also produced at large scale. So when we will start to produce at large scale, the cost will decrease. But for the moment, we need to invest. So it is the capex is very high. So this is true. There is no choice. And we know also that if we change our energy system, the consequence for the next year, if we will have a big peak of CO2 emissions. Why? Because we have no ammonia, no hydrogen, no e-fuel, no sufficiently for use as fuel. So it means what we will do, we will use natural gas, petroleum, and so on, to build old plants, to build many things. So we will have a big peak of CO2 as consequence.
And I have another question.
Yes?
My last question. The problem of the oxides of nitrogen is, it could be very important in the ammonia combustion. So today the catalyst is a challenge to get the best catalyst.
Yes.
Yeah?
Yes, it's a big challenge.
And what are the materials
so for the moment, there is, I try to find, I think there is 2 or 3 studies only about that. Because there is no real decision to say, okay, we will use ammonia as fuel. There is some announcement for marine sector, but it is announcement. So for the moment there is no real engine. There is not all set up around the engine. And I only see one catalytic reductor, not for NOx, it's for NH3, because under NH3 is worse than NOx. NOx, I think we can manage with a selective catalytic reactor. But when we have a selective catalytic reactor, we need after to reduce ammonia. Okay? And the problem is it's really very low TRL knowledge for the moment, and I only see one system in Japan where they study, in fact, burner for gas turbine, and as they try to optimize the burner, sure, they don't use only optimized regime, they try. So in fact, there is a kind of cheminée, and there is a big catalytic reactor here to reduce ammonia. And this is a patent, I don't know more. So, you know, so it's, we have a lot of challenge on that. Why also? Because I told you that there is NOx, but there is also N2O. And N2O also can change the life of a catalyzer. It has to be also considered. So this is very complex. And also about a selective catalytic reactor is nice. It's reduced NOx, but the drawback, it's produced also a little bit N2O that we want also to avoid. So, you know, there are plenty of work on that.
Thank you very much.
Okay. Yes?
The last question.
Yeah, actually it's a very nice presentation. So I want to ask you the general questions. So how you are producing the ammonia? Which method you are using to produce the ammonia?
I don't produce ammonia, I buy bottle.
Yes, you do not know.
You know, I call air liquid.
No, actually.
And sometimes they can give me bottles because 2 years ago there is a lack of bottle due to a problem with agriculture, so there was no ammonia. So okay, we don't produce it. For the moment there is no power plant which produce ammonia in green. Okay, we produce ammonia only from hydrogen, and ammonia is and hydrogen is produced through formage of natural gas.
Okay.
For the moment, there is no green ammonia.
Okay. And one more question. Actually, compared to the fossil fuels, so what's the efficiency of the ammonia engines? So what is the efficiency? So means transportations. How long we can use? How long we can travel using the ammonia engines?
How long in what terms? How long in?
Means say if we are using the fossil fuels, we can travel maybe 100 kilometers per liter.
Yes, this it's the fight between people who do fuel cells and people who do thermal engines, because we say no problem, we can run 100 years. It's not the case with fuel cells. Okay, so fuel cells efficiency is higher at the beginning. Sure, that thermal engine, 35% globally is not like a fuel cell, no difference. But what is good for thermal engines, it's as function of the duration, there is no change. And also it's old technology, so we know very well it. It's not the case for fuel cells. There are so many questions that we have to resolve. So I don't say that it's better one or one, but it will be function of the use. For example, there is a lot of, so there is a big program in France about hydrogen. It's a fashion of hydrogen. And it started 15 years ago first, and it was only about fuel cells. Okay, only about fuel cells. If we talk to people on the road about hydrogen engine, it's fuel cells, it's not thermal engine. And we just start to change the mind by showing that, in fact, in the trucks, in big lorries, fuel cells is not reasonable. It's better to have, in fact, classical hydrogen thermal engine. And we just change, it's less than 2 years. Okay? I don't know if you already see a Mirai car. I don't know if there is Mirai car. There is no hydrogen in Chile on the pump. So Mirai car is the first fuel cell, hydrogen fuel cell car of Toyota. And in fact, it's incredible because if you look on the car, you have, hydrogen tank. It's important. Hydrogen tank. You have fuel cells. You have battery. Okay? And you have electric engine. So in fact, wow, there is no place. Okay, so always it's the same for marine and so on. It depends of the use, it depends of the size, it depends of the distance. I don't say, for example, that electric car is stupid. I'm convinced that electric car is the solution for big metropole, for cities and so on. In France and in Europe, we have a new law. It's called zero carbon emission city. So in 2024, it is not possible to be inside any big city. Big city, it's 200,000 people with diesel car. It is totally forbidden. No particulate matter. They don't want. It's finished. Okay? CO2, it will be the same. So only electric car inside the city. But there is another problem about countryside. People who live in countryside, they cannot use electric car because it's a short distance that you can do many things like that. So always we have to consider one solution, the best solution for each problem. So
Ok, agradecemos a la presentación, señora Cristina Busser.
Merci.